Mr. Kostas Nikolaou. He is a chemical engineer with nearly 25 years of experience in specializing in waterproofing, insulation, and provision of services for the design, planning, and installation of energy management and energy-saving solutions in residential and non-residential buildings. Currently, a postgraduate student of sustainable design of the building's indoor environment in the School of Applied Arts and Sustainable Design of Hellenic University. He is going to present us a socially oriented use of abandoned building at nearly zero energy consumption building of senior housing. Oh, excuse me, field assessment of indoor environmental quality and energy consumption in Hellenic building.
Thank you. Good afternoon. This is the title of our work. It's the field assessment of indoor environmental quality and energy consumption in a Hellenic dwelling. In Greece, residential buildings are responsible for almost 30% of the total final energy consumption. The cost for the energy for the houses is increasing. That makes the homeowners to sacrifice thermal comfort and also indoor air quality. And this is the worst thing which can be done, because we are in Greece, we are having more and more houses with reduced indoor environmental quality. We are trying to investigate what's happened in a typical dwelling and looking for three factors. These factors are the thermal comfort, the indoor air quality, and the energy consumption. We are interested in with all these three factors to investigate. The final goal is to find the best indoor, how we can have the best indoor environment with the least energy consumption. Now, in order to do this, we are collecting data from the dwelling for about a year. The data are indoor and outdoor, and they are the typical temperature, relative humidity, plus CO2, PMs, and volatile organic compounds. And of course, the energy consumptions of a lot of devices in that houses. This will run for a year, and we also run various scenarios of the using of the systems of that flat, of that house. Now, the dwelling we are choosing is a typical household, family of three, about 120 square meters, renovated at 2021. It's class B, B+, according to the national regulation of energy consumptions of building, and the heating system is hydronic with natural gas boiler and radiators with thermostatic valves. For the cooling, they are using 5 AC split unit types and 3 floor fans. Now, domestic hot water is with classic solar water heater and a natural gas boiler. Now, the ventilation is installed a central mechanical ventilation heat recovery system. The filters are MER 13, and the heat recovery is about 92%. For the air tightness, the building, after a blower door test, has 1.84 air changes per hour at 50 Pascal. This is a floor plan which shows the position of radiators, ACs, fans. The blue and red rectangles are the exhaust air vents and supply vents of mechanical ventilation system. And you also see that we have a lot of temperature and related humidity sensors, plus 5 inside the building, 5 CO2 sensors and 2 or 3 PM sensors. Outside of the building, we are having also CO2 PM sensors and a meteorological station on the roof of the building. We are collecting this data for this building for the year. We start from April, so we already have data for the summer. We also collecting data for the energy consumption of the air conditioning units, the fans, the mechanical ventilation. The data are per hour, and some of them are per day. Now, where the scenarios are for heating, cooling, and the ventilation. We combine different mixing of these three in order to find the best solution during summer and during winter. Till now, I have only some preliminary data, and I will show you some of them. Now, this is from 1st of April till 8th of August, the temperatures outside of the building, the thick blue line, and all the other rooms of the building. You can see that till the end of May, we have almost the same behavior in all the rooms. They are about 25 degrees of Celsius, and from the end of May, you can see an increase in the outside temperature. That means every user of the house is free to choose the way he will cool the room he occupied. We already see some lines goes below the others. For example, the yellow line the end of March means that somebody wants a lower temperature in his room, so he turned on the AC device. Now, for the first 2 months, from June to the end of the July, we are using the ventilation system. During the day, it's mechanical ventilation, but during the night, when the conditions are acceptable, we are using natural ventilation. When the conditions are not acceptable, they are not acceptable if the temperature outside during the night is above 27, 28 degrees of Celsius, if we are having a wildfire or a dust from, let's say, from Africa. And of course noise, but the noise was not the case in this summer in any of the rooms. Every user from 1st to end of June uses only the air condition, but from the 1st of July, they are allowed to use the fans. The fans was the first measure once somebody feels uncomfortable. That means in the 2 bedrooms and in the living room, they are using the fan first, and then they add the air conditioning system in order to have the condition they prefer. From August, we have run 3 different scenarios, and I will show them in the next slide. In this slide, you can see again the outdoor temperature, you see the variations, and the temperatures in all the rooms. The black lines represent the daily energy consumption of the cooling system, means the air conditioner and the fans. The consumption was about 20 to 30, close to 30 kilowatt hours per day for the systems. Now, these are the 2 scenarios we ran. The first, of the 5th of August, we turn on the AC, the air conditions, 24 hours a day till the end of August. For the first 6 to 7 days, air conditioning, fan, and mechanical ventilation were turned on, and the temperature in the room was set up about 28 degrees of Celsius, with the exception of the study room, because there is no fan, so we allowed that room to have the temperatures at about 26 degrees of Celsius. Now, the second scenario is without mechanical ventilation. We are still running under air conditioning system, but now if the CO2 inside the house exceeds the 1,500 parts per million, we are opening the windows for, on average, half an hour, turning on the AC system. And then, after the levels drop below 500 parts per million, we close the windows and we turn on the AC system again, and the fan. Now, the last part of the third scenario is the last 5 days of August, and there we are not using the fan at all. We run only under mechanical ventilation, and the ACs now the set point is that in order to have 26 degrees of Celsius in almost every room. Because we make the hypothesis that without the fan, we have to reduce the temperatures in order for the users to feel comfortable. Of course, for this period, all the users of the rooms, they fill questionnaires about what they are feeling, but it's not included in our presentation. And for the energy consumption, you can see that on average, we don't have big differences. We're about 20 kilowatt hours per day. The last 3 days of August, we exclude the last 3 days of August because we have a drop in the outside temperature, and that makes the consumption to be even below 10 kilowatt hours per hour of electrical energy. Now, about the air quality. We know that we are using the CO2 for two reasons. The first is as an indicator of the indoor environment. How contaminated, we can make a first evaluation of how contaminated is the indoor environment. And of course, if the concentration exceeds some points, we can say that it's a pollutant itself. In this house, the system, we are running under mechanical ventilation. Now, we are using a COC sensor inside the exhaust air of the mechanical ventilation, which means that we know the average CO concentration of the building. We are trying to keep this below 800 ppm. That means when the concentrations is above 200 ppm, the system works in higher speed, and for this building, that means from 160 cubic meters per hour, we increase the speed, and we are having 200 cubic meters per hour. This remains till the concentration of the CO2 drops below 700 parts per million. But this is just an average. The problem is what has happened when we have closed doors. When we are running a mechanical ventilation system, we always have an undercut under the doors. But this undercut is not enough. I will show you a small example. This is the study room. Many hours is with a closed door. The thick black line is the concentration of the CO2 outside, and you can see the variations in the CO2 concentrations in the room. For example, every 1 or 2 hours, the user of the room goes out of the room, leaves the door open, the CO2 concentration drops, and then he went back to the room, closed the door, and so on. Because the flat is running under mechanical ventilation, you see that we have some peaks, but we are never above 2,000 ppm. We have some peaks close to 1,800 ppm. But imagine what can happen in a bedroom. what's the difference of the bedroom with a closed door compared to this? Is that when you go to a bedroom and you fall asleep, you never wake up 3, 4, 5 times during the night over the door. And imagine if 2 people are sleeping in a bedroom, we can have concentrations of CO2 even under mechanical ventilation systems, which will exceed 2,000 parts per million. If we are not running a mechanical ventilation system and have closed doors, we can easily see a concentration 3,000 to 4,000 parts per million with a closed door for about 4, 5, 6, or 8 hours. Now, for the last data I want to show you is that this is the kitchen of the room. It's 3 days ago, it's the Sunday of 17th of November. It's, now we can see at about 5, 6 o'clock in the afternoon, first drop on the CO2 concentration. Then the concentration of the CO2 rise up again. It's this is the drop. Then the concentration of the CO2 rise up again, and then again we can see that drops till 10 o'clock in the night. Somebody may say that, okay, this is a positive result. For some reasons, we have less CO2 from 900 ppm to, let's say, about 700 ppm. This will be the conclusion if in that flat you have only CO2 sensor. These are the PM 2.5 in the kitchen. At the same time, what we are looking here is first at about 5 o'clock in the afternoon, we turn on the range hood. The range hood is a special installation. The fans are not inside the box of the range hood. There is a fan outside of the building who runs at about 900 cubic meters per hour. And we leave only the box with the filters inside the house. The reason is that we want an increased airflow, the first, and the second is the reduction of the noise. Many users are not using the fan because of the noise, so we want to reduce the noise. Of course, you cannot find 900 cubic meters in a flat like this, with air changes at 1.8. So we are having a hole at the wall down of 2 meters down of the position of the range fan with a damper. So when we turn on the range hood, the damper goes and allows outside air to come inside unfiltrated, without any filtration. The most part of this air goes up because of the fan we have installed, but we always have some part of that air will spread inside the kitchen. And this is why when we open the range hood, we can see the increase in the PM 2.5 and the decrease in the CO2. Now, the first decrease of the PM 2.5, which is here, this happened not because we closed the range hood, but because we turn on a do-it-yourself, let's say, air fan, which the name of this is CR box. It's called Rosetal box. It's a simple square fan it's a cube with a square fan on the top and 4 filters around. The filters are on the sides. The filters are BEF13, and there's a cardboard on the bottom just to fill the hole. You can see the reduction in the PM2.5 concentration. Now, after half an hour, we turn on the range hood again. Again, we have a reduction. You can see again the same pattern, reduction in the CO2 and increase in the PM2.5 concentration. Again, run the CR box and you can see that the result of this. Now, I said only that we have allowed outside air to come inside the house. But this is not a problem by itself. It's a problem because it's happened during the night. And the problem is this. The yellow line is the outside concentration of the PM2.5 in this area. So, in Greece during evening, in Athens, during evening, during night, you must be very careful when you walk outside because you have high concentration of particulate matters. This map shows at 10 o'clock at that evening the USA EMEA 2.5 air quality index in Athens, and you can see how high are the numbers. Now, what we are doing, we are monitoring the operation and the indoor condition of that flat. We are assess the thermal comfort, the air quality, and the energy consumption. We want to see all these three factors together. And we are under different operating scenarios. We found correlation between these factors, and we identify proper operating solutions and good practices. The final target, best indoor conditions with least amount of energy, this is what we want to investigate. And for the end, just to say that this is part of my master thesis in sustainable design of the building indoor environment program, which is a unique program, and I feel very happy that we have this program in Greece. Finally, I want to thank my teacher and professor and supervisor of my work, Mr. Balaras. I think I owe him this thanks. Now, thank you very much for your attention.
Thank you very much, Mr. Nikolaou. Do you have any questions? No? Okay. Okay.
Hello. How easy is to install all these sensors and all these meters in an existing house?
All the sensors are low-cost sensors because we are not interested in the accuracy of 1 parts per million or of 1 microgram. Now there are in the market a lot of products. The difficulty is not to install the product, the sensor. The difficulties are how you collect the data, because each system has differences in the way you can download the files, you can, the time limit, some give you 5 days time limit, some other sensors are giving you 1 month time limit to download data. This is a hard work. The other part is the dashboard. Because they are not all the sensors in the same ecosystem. We have that products, but this is not the case. You have to programming and find and build a dashboard in order to check and all the sensors and all the data and see the difference between them. It's very difficult, but I think in the future this will not be the case.
So please, we are running out of time.
Okay, maybe we can have...
We can talk outside. Thank you.
Thank you.
Thank you very much.